In this problem, we're asked to look at this frame, which is supporting a drum. The drum has a weight of W. This frame is pinned to the ground at C. There's a roller at B. We want to know three things. One is the axial stress in that member HK at the top. We want to know the normal and tangential components of the stress in that member where theta represents the angle of a splice in HK. And we want to know the shear stress in pin J on the frame where we see that this pin is a single-sided connection between the two members of the frame. Before we start though, what I would like to do is do a little bit of trig. For example, this angle of phi, we're going to use that. Phi is going to be the inverse sine of 0.3 L divided by 0.5 L. That is, this distance here is 0.5 L. I'm sorry, not 0.5, but 0.3 L. And this hypotenuse is 0.5 L. So that gives us that usual 36.87 degree angle. We're also going to use a dimension here. I'm going to blow it up just a little bit to make it more clear. But if we look at this right triangle right here, where this angle is phi, this is the radius of the drum, which is d over 2. And what I'm going to need later on is this distance there of b. So if I look at the trig here, is that I will have that the tangent of phi is going to be equal to the opposite side of that triangle, which is d over 2, divided by the adjacent side, which is b. So from this, I can solve for b, where b is going to be equal to the diameter of the drum divided by 2 tan phi, which we just found. So we've got phi and we've got that. I'm also going to do some equilibrium analysis on the frame as a whole. So if you will allow me to draw the FBD right here on top of this here, the roller is going to be BY, the pin is going to be CY, and the weight of the drum is W. So from this one FBD, if I make this X and then this Y, if I do a summation of moments about B, I have CY, which has a moment arm of 0.3 L, weight, which is going to have, I'm sorry, that's going to be 0.6 L, and W, which is going to be 0.3 L, and it's going to have a minus sign in front. So for equilibrium, we see here that the reaction force at C is simply going to be half of the weight. Where when I sum forces in Y, I get the reaction forces there at BY and CY minus the weight. And from this, I see that BY is also equal to W over 2. So that helps me find those reactions. Now what I'm going to do is draw a free body diagram of the drum. Like this, and I'm going to draw a free body diagram of this member of HJC. So the forces I'm going to draw on the drum, there's going to be this normal contact force, which I'll just call F, one on each side. That's going to be at an angle of phi from the horizontal. And of course, then the weight. Then when I draw the free body diagram of this member of HJC, what I'm going to have here is the normal force in. It's normal, perpendicular. There's that distance B that we just found. The force HFHK, which is what we want to find. Since there's a pin joint at J, there's going to be both an X and a Y component. And then there's the value of CY, which we just found right above. If I look at the drum, summing forces in the drum in the Y direction, minus W plus F cosine phi. And since there are two of those, when that is set equal to a 0, I find that the force that the drum puts on member HJC is going to be the weight divided by 2 sine phi. Okay, so that's all known information. Now I'm going to look at member HJC. First thing I'm going to do is do a moment about J. Moment about G, CY, the reaction force there on the right side, has a moment arm of 0.3 L with a plus sign. The drum force there, F, as we just found B, that's F times B with a plus sign. And then HK, remember HK is going to be putting a force on there of F HK with a moment arm of 0.4 L, and that's going to be in the minus K direction. So from this, I have an expression for the load that's carried by HK, and that's going to be 0.3 CYL plus FB. We just found CY and F and B, so we can substitute those into here. And when I do, the result that I get for HF sub HK is going to be 0.3 divided by 2 WL plus 1 over 2 sine phi, putting in the expression for B, that's D over 2 tan phi, W, then of course there's going to be a 0.4 L there. So that gives us, in terms of things that we know, what the load is that's carried by member HK. We're also going to, while we're at this, we're going to sum forces in X and Y, where we have FHK plus the X component of the reaction there at J minus F cosine phi. From this equation, I see that the X component of that reaction is going to be F cosine phi minus FHK. I sum forces in Y. I get CY plus JY, the Y component of the reaction there at J, minus F sine phi. Again, I'm just looking at the FBD and writing down this equation. I see that the Y component of the reaction there at J is going to be F sine phi minus CY, and all this is in terms of things that we know. So we know JY and JX. So what we would say then is that the shear stress I'm sorry, the normal stress, the axial normal stress, would just then be FHK divided by A. For part B, though, what we're really asked to find is, what if there's a splice in HK? What if that splice, there's a glue joint, and we're concerned about the normal and the shear components of stress in that glue. That splice is at an angle of theta, and we just found FHK, so we know this axial load. But what we want to do is project this onto normal and tangential. So the tangential part of this resultant here, I call FT, and the normal component is what's going to produce our shear and normal components of stress. So we first want to find Fn and Ft, and then from that we can calculate sigma and tau. So just from projections, the normal component is going to be FHK, and that's normal to that face, times cosine of theta. So theta is here. So Fn, which is this this amount right there, and looks like I have written down the wrong trig function. This would be sine of theta. And the tangential part, just looking at trig, that's going to be FHK times cosine. The area of this at this splice is A divided by sine of theta. So therefore, sigma n is going to be equal to FHK divided by let me try that again. That's going to be Fn divided by A over sine theta. And so that's going to be FHK times sine squared. This says that our shear stress, that is the stress component that's tangent to that splice, is going to be Ft over the area over which it acts, and that's A over sine theta. So that's going to be FHK sine theta cosine of theta. So that's the normal and tangential components of stress that we have along that splice. Lastly, what we want to do is look at that joint J. What we saw was acting on that pin were the reaction components of Jx and Jy. We don't really care about Jx or Jy individually, but what we care about is the resultant of those two. So J is simply the magnitude of that reaction. So that's square root of Jx squared plus Jy squared. And that's balanced out by the shear force from that single-sided connection. So J is equal to V for equilibrium. What we've seen before is that the shear stress in the pin then is equal to V divided by the area over which that shear force acts. So that's going to be pi d over 2 squared, where d is the diameter of that pin. So that's going to be equal to 4 square root of j x squared plus jy squared divided by pi d squared. So we were asked to do a lot of work here. One, we did considerable amount of effort there trying to find the external reactions acting on the frame, Cy and By, finding the normal force that the drum exerts on that member there, HJC, F. We use that same, or we use the FBD of HJC then to find the load that's carried by member HK. Other equilibrium gave us the reactions there at the pin. But then we went to part B and we looked at the projections of HK, FHK on the normal and tangential plane of that splice in order to get the normal and tangential components of stress. And then we looked at the shear force in the pin, and from that we extracted the shear stress.